Okay, so we're going to continue with the acid-base review. And we're going to focus on calculations for this one. Okay, and most of the calculations, or I guess all of the calculations with acid-base, go back to or at least in aqueous systems, go back to the one concept that water self-ionizes into both the hydronium and the hydroxide ion. Keep in mind that the change in enthalpy for this is greater than 0, which means that this is an endothermic reaction. Okay. So the ionic product of water, Kw, so this is an equilibrium constant, is concentration of the hydronium times the concentration of the hydroxide ion. This is equal to 1 times 10 to the negative 14th for temperature equal to 25 degrees Celsius. This does change depending on the temperature. Alright, pH equal to the negative log of the hydronium ion. pOH is similarly the negative log of the hydroxide ion. Okay, if I'm looking for the hydronium concentration, it is going to be 10 to the negative pH. If I'm looking for the concentration of the hydroxide ion, given the pOH, 10 to the negative pOH. Okay. pH plus pOH is going to be equal to 14. The Kw is equal to the Ka times Kb, okay, and this means that pKa plus pKb is equal to pKw. Okay. I want to take the time to write an equation for HF plus water is going to set up the equilibrium to be the hydronium ion plus the fluoride. Okay, this will be covered. Your Ka then is going to be your hydronium ion times the concentration of your fluoride over the concentration of HF. Okay, if we want to write the similar equation for the system acting as a base, we would write the fluoride ion plus water, setting up an equilibrium with HF plus the hydroxide ion. This will be covered with Kb equal to HF times the concentration of the hydroxide over the concentration of the fluoride ion. All right. If I add those or multiply those together, Kb times Ka, you should be able to see that this will end up being this equation, which is Kw. I want to point out that it is not just the inverse of one to the other. I didn't just inverse this equation to get this one. It's actually taking this anion and seeing what it's going to do when I put it with water. Okay. Okay, so Kw actually changes with temperature, and we would see a reaction or a relationship like that. So at 80 degrees Celsius, just to give you an example, the Kw is 2.0 times 10 to the negative 13. Okay, concentration of the hydronium ion at that temperature is then Kw to the 1/2, or the square root, which is 4.47 times 10 to the negative 7th molar. Okay, so if we look at pH and pOH, some calculations. Okay. Strong acids completely ionize. So if we are given a concentration of hydrochloric, it's going to be equal to the concentration of the hydronium ion in solution because it completely ionizes. So if we have a pH looking for the pH of 0.1 mole per decimeter, negative third of hydrochloric. This is going to be equal to negative the log of 0.1. pH would be 1.0. Sig figs. Remember, in sig figs, the number of sig figs in the concentration should be equal to the number of places following the decimal point. I can't spell following. Following the decimal point in the pH. So for this concentration, I have 1 sig fig. So I have 1 digit beyond the decimal point. Okay, for a strong diprotic acid, okay, the IB lets you assume that this fully ionizes. So you're going to assume that both H pluses fully ionize. Okay, so for example, if you had sulfuric acid, you're going to assume it completely dissociates into this. So the concentration of your sulfuric is going to be the concentration of your H plus. Okay, this simplifies the calculations. Okay, in reality, the second hydronium is really going to be in an equilibrium. Okay, with the Ka and all those calculations that come with it. However, you can simplify it for the IB for a strong diprotic like sulfuric. And that ends our screencast. We're going to do some equilibrium problems with acid bases next.